Hello, so in this video today, we're going to differentiate the function, the modulus of sec of x. So as with previous videos, to differentiate this function, we're going to need the chain rule, and we're going to need our knowledge of how we differentiate these two functions. So firstly, the modulus function. So when we differentiate the modulus function, as we showed in a previous video, we get the modulus of x divided by x. And when we differentiate the sec function, so sec of x, when we differentiate that, we get sec times by tan. So these are two results from previous videos. So previous videos, and using these results, we can use these results in this example here. Previous videos. Okay, great. Yeah, so this is going to be a case of using the chain rule. So yeah, let's do this on a new page. So if we differentiate this function, modulus of sec of x, this is the same as differentiating the modulus of sec of x with respect to sec of x, and then multiplying this by the derivative of sec of x with respect to the variable x. And then, yeah, this is just an application of the chain rule formula. So chain rule. And then we can go ahead and differentiate this. So differentiating the modulus of sec with respect to sec, that's just going to be using this result here, the modulus of sec over sec. So the modulus of sec over sec, and then multiplying this by the derivative of sec of x with respect to x. So we know that this is just sec times by tan of x. So then we get sec times by tan of x here. And as you can see now, we can just actually cancel out the sec here and here. It's just cancelling that out with that. And so we're just going to be left with tan of x times by the modulus of sec of x. So that's our result for this derivative. Let's just consider the domain of x values in which this derivative holds true for. So in order for this to be defined, so in order for this modulus of sec x derivative to be defined, so this is defined when, so when the modulus of sec, or when sec does not equal 0, so this is defined when sec does not equal 0. Obviously sec does not equal 0 for any x value, because sec is always, I mean, a graph of sec looks like this, roughly, of 1 there, an asymptote here, -1 there, asymptote there, this repeating kind of periodic sequence of functions. So yeah, so sec is never actually equal to 0. So it's defined when sec x does not equal 0, and also when sec x itself is defined, and when sec x is defined itself. Because obviously we have these asymptotes here, so we just got to make sure that sec of x is defined itself. And where is it defined? So it's defined basically when x does not equal these x values of these asymptotes here, so pi over 2, 3 pi over 2, 5 pi over 2, and so on, and the negative ones as well, so negative pi over 2, negative 3 pi over 2. So these basically these odd multiples of pi over 2. So sec of x is defined, and this is defined when x is between, so between 4, well, between, yeah, so between minus pi over 2 up to pi over 2, between pi over 2 up to 3 pi over 2, and so on and so on. So yeah, these are these odd multiples of pi over 2. So 2k minus 1 times by pi over 2 up to 2k plus 1 times by pi over 2. So this is the values of x for which this is defined for. So therefore we can just conclude then that d by dx of the modulus of sec x is equal to tan of x times by the modulus of sec x, and this is defined when x is between these odd multiples of pi over 2. So defined when, let me write that again, defined when x is between, so 2k minus 1 times pi over 2 up to 2k plus 1 times pi over 2, where k is just an integer value. And yeah, so using the graphs here, we can just check that x has to be between these values here in order for the function to be defined itself. So yeah, that concludes this video, because we get this this result here, which holds true for these values of x.